All right, let's talk about theoretical and experimental probability. 17.1 of the textbook. There's a little bit of vocab here. A probability experiment is an activity that involves chance, such as rolling a number cube, drawing a card out of a deck, that sort of thing. Whenever we have a repetition from the experiment, each of those is called a trial, and the outcome is what the result is from that trial. The set of all possible outcomes in an experiment is called the sample space. For example, if you're rolling a die, a standard die, the sample space consists of the numbers 1 through 6. And then a subset of the outcomes from the sample space is called an event. So, like I said, for the sample space of rolling a standard die, the options are the numbers 1 through 6. We typically write a sample space with these curly brackets and then just a list of all of the possible outcomes with commas in between. In an event, let's call this event A. Event A is rolling an odd number. So from the dice, choosing which of those are odd numbers, your options are 1, 3, and 5. And again, we list those with the curly brackets as a set of numbers, a sequence, if you will. With that, we can have the theoretical probability. That is when all of the outcomes of an experiment are equally likely, then the theoretical probability of an event is given by this formula here. So P of A stands for the probability of event A. And that formula is the number of outcomes that exist in event A divided by the number of outcomes in the sample space as a whole. So if we go back and talk about event A being rolling an odd number out of a standard die, you have 3 options in event A, 1, 3, and 5, out of 6 total options in your sample space, 1, 2, 3, 4, 5, 6. So you have 3 divided by 6, or 1/2. So theoretically, you have a 1 in 2 chance of rolling an odd number each time that you roll a standard die. So we have this spinner. It is all of the numbers 1 through 12. They are equally spaced. In this case, the sample space of this experiment is a list of all of the numbers 1 through 12. You got your curly brackets, you got your commas. And it says, are all of the outcomes in this sample space equally likely? Why or why not? And that's dependent upon the size of each little piece of pie here. So because each sector is the same size, then the chance of landing on each number is equal throughout the entire spinner. And then in this next part, it says, what is the set of outcomes A for the event of spinning a prime number? So event A is spinning a prime number. So you'd look at your options 1 through 12. You'd pick out which one of those are prime numbers and you would list them. So all of the prime numbers between 1 and 12 are 2, 3, 5, 7, and 11. So yeah, that's our set of outcomes for this version of event A. Keeping that same spinner, it says, what is the theoretical probability of spinning a prime number? So again, we had 2, 3, 5, 7, 11. So we have 1, 2, 3, 4, 5 options out of the 12 total. So because there are 5 possible prime numbers and 12 total options, the probability of rolling or of spinning a prime number is 5 out of 12. What is an event for spinning the spinner whose theoretical probability is 1 in 4? So in this spinner, I want some sort of event that has a 1 in 4 chance. There are a couple options you could choose here. One of those being maybe you're going to spin a multiple of 3, right? 3, 6, 9, 12. That has a 1 in 4 chance because there are 4 options in the subset in the event out of 12 total. 3 out of 12 reduces to 1 out of 4. Now it asks for something that has a theoretical probability of 0. So what is not going to happen from this spinner? So that might be the probability of spinning a 13, because that's not an option in this spinner. And then something that's like it's something that has the probability of 1, a theoretical probability of 1. That means there is a 100% chance that you will land in this event. So for example, you might choose a natural number that's less than 13. The natural numbers start at 1, and they're basically all of the positive integers. 1 through 12, those are all less than 13. So that's an example of something that you would have a 100% chance of landing on. So its probability is 1. Then we can have experimental probability. the theoretical probability of getting a 3 on a number cube is 1 in 6, right? There's only 1 3 out of 6 total options, which means you can expect to get a 3 one time for every 6 rolls. But let's say you're rolling this number cube 600 times. You probably won't get a 3 exactly 100 times. Okay, so from there we have our experimental probability, and it has its own formula as well. We still use the same notation, the probability of event A, P of A, which would be the number of trials, so the number of times you actually do the thing, where event A actually does occur, out of the total number of trials completed. Okay, so let's look back at our spinner here. What is the theoretical probability of spinning an 11 for one spin? So in theory, not having actually done the experiment, there's one 11 piece of pie out of the 12 total options, okay? And we're doing this 60 times, okay? We are spinning this spinner 60 times. So the theoretical probability of getting an 11 out of one spin is just 1 out of 12. But now it's saying if we spin it 60 times, how many times do you expect to spin an 11? So from there, we take the probability of the event times the number of trials. That's called the expected value. Okay, the expected value is the probability of the event, if we had done it once, times the number of times that it's actually going to happen. So I have a 1 in 12 chance if I do this once, and I'm doing it 60 times. So I expect to get an 11 5 times, okay? If the experiment comes out perfectly. Now you can see here underneath the spinner that we have the actual outcomes for somebody that spun this 60 times, and maybe we got 11 5 times, maybe it's more, maybe it's fewer. It just depends on the spin. Not every outcome is going to come out perfectly, okay? So with that, it says, how many times did you actually spin an 11 in 60 spins? What is your experimental probability? So looking at this table here underneath the spinner, you would count the number of times that the 11 shows up. In this case, it shows up 7 times. So we actually spun it 7 times. That means our experimental probability is that formula that we talked about a few slides ago, where how many times it did actually happen. So in this case, it happened 7 times out of the total number of times that we spun the spinner, which is 60, okay? So our experimental probability is 7 out of 60. This is what actually happened, not what should have happened, okay? So it says, compare the theoretical and experimental probabilities of spinning an 11. Does the theoretical, what should have happened, overestimate or underestimate the experiment, okay? So the theoretical was 1 out of 12. And if I get that to be a common denominator of 60 because of the 60 spins, that's equivalent to 5 out of 60. But what actually happened in this case was it was 7 out of 60. We got the 11 7 times. So 5 out of 60, clearly less than 7 out of 60. That means that this theoretical probability was an underestimation. It underestimated what actually happened in the experiment. We're keeping the same spinner, and now we're spinning it 600 times. But we're not going to do any calculations right now. It says, would you expect your experimental probability of spinning an 11 to be closer to or farther from the theoretical probability after 600 spins? So we had 1 spin and it was 1 out of 12. We had 60 spins and it ended up being 7 out of 60. Do you expect the theoretical probability after 600 spins to be closer to or farther from your experimental probability? So what that means is as you're spinning more and more, do you expect to get closer to what the theoretical probability actually should have been? So in general, we should expect it to be closer to the theoretical. The experimental should be closer to theoretical because as you have more trials, more and more trials gets you closer and closer to what the theoretical probability should be, what you expect to happen, right? If I only spun the spinner twice, I don't expect to get an 11 perfectly adjacent to those 2 spins. But if I spend 20 times and then 50 times and then 100 and then 300 and then 600, I get closer and closer to what I expect to happen. A little bit more vocab. We can also talk about Venn diagrams here. So here's some examples of Venn diagrams. And in those Venn diagrams, we have something called an intersection. And it's denoted by this like upside down U shape. So if you remember from domain and range, we have the union, which is a regular looking U, which we'll talk about in a second. Its kind of opposite is the intersection. It's an upside down U shape. And it stands for the word and, mathematically. So A intersect B is the same as A and B. And then the union, which you have seen in domain and range, is A or B, so it has that regular U shape. So if we think about what this looks like on the Venn diagram, an intersection is where the two events overlap. Okay, so here in this Venn diagram, S, the big box, is your entire sample space. And then you have event A and you have event B. The intersection is how they overlap. Okay, and then the union is all of A and B combined, or A or B, I should say, all of that combined. So if I have two events and I could get something from A or I could get something from B, the union is represented by that entire space that's filled in here. We can also have something called the complement. So in one instance, the complement of A is denoted as A with a superscript, or it kind of looks like an exponent, A superscript C. The C stands for complement. And that basically means everything that's not A. So the complement is not A. So in this case, if I'm looking for the complement of A, I'm looking for everything outside of that A space. And this should actually also be covering the part of B that doesn't overlap with A. So I'll go ahead and shade in the section of B that does not overlap with A. So not the intersection, but the rest of B essentially. So suppose you spin the spinner below, still the 1 through 12 is the same spin as before. Event A is getting a multiple of 3, and event B is getting a number less than 8. So we're going to draw this Venn diagram. A represents all of the multiples of 3. B represents all of the numbers less than 8. Okay? So in this case, A is my multiples of 3. B is my numbers less than 8. I'm making my box. I need to always have it in a box because there are some cases where you have values that are not part of event A or event B, but they're still in your sample space. So here we have this entire box S, the entire sample space. Event A consists of multiples of 3. Event B consists of numbers less than 8. So at first I'm going to find the complement of those two events. So I'm going to find all the values that are not multiples of 3 and also not less than 8. So my options are basically 10 and 11 and 8, actually, because 8 is not less than 8. So I'm putting those outside of the two overlapping ovals, because those are still in my sample space, but they're not part of event A or B. The intersection of A and B would consist of multiples of 3 that are less than 8. So both of those things happening at once. So that includes 3 and 6. The other multiples of 3, but that are not less than 8, are 9 and 12. So those are only in the oval for A that's specific to just A. And then all of the numbers less than 3 that are not multiples of 8, so part of B but not part of A, are 1, 2, 4, 5, and 7. So they exist in the B section. Okay, so there's your Venn diagram. And keeping with that, we're going to make sure we understand the notation here. So first I'm finding A and B. So it's the intersection of A and B. And here's our Venn diagram again, just so we can refer to it. The intersection of A and B would be the integers from 1 to 12 that are both multiples of 3 and less than 8. So both of those things happening simultaneously. So in this instance, that's 3 and 6. It's asking us to describe what these mean, not finding what the values are necessarily, but these are integers from 1 to 12 that are multiples of 3 and also less than 8. The union, A union B, A or B, consists of all of the integers from 1 to 12 that are a multiple 3 or less than 8, and it could be both, or it could be just one of those events. So everything that's inside of either of the two ovals is part of this union. Okay, the complement of A is the integers from 1 to 12 that are not a multiple of 3 specifically. So everything outside of, completely outside of oval A. And then the complement of B are all of the integers from 1 to 12 that are not less than 8. So everything outside of oval B. So 11, 10, 8, 9, and 12 are all part of the complement of B. Okay. Same spinner as before, same Venn diagram as before. Now we're going to find probabilities of these intersections or these complements or the unions. So first I'm finding the probability that I get a 3 or a 6 or a 9 or a 12. This is just a 3 or a 6. This is the intersection for this first one. So I have a 3 and I have a 6. Those are the only two values in the intersection where the two ovals overlap. out of my 12 total possibilities from the spinner that was 1 through 12. Okay, that's the intersection. And you could simplify this if you want to, up to you. It's just more room for error. I'm happy with 2 over 12 for purposes of probability. Then if I'm finding the union, that is everything that could be in A or could be in B or could be in their overlap. Okay, so that is 9, 12, 3, 6, 1, 2, 4, 5, 7. All of those are the options for the union. So we have 9 options there out of 12 total. If you would like to simplify that, that's a 3 out of 4 chance. The complement of A is everything that is not in oval A at all. So that's everything that's outside of both ovals, 11, 10, and 8, as well as the things that are strictly in B, 1, 2, 4, 5, and 7. So I have 8 options out of 12 total, which reduces to 2 over 3. And then finally, the complement of B is everything that's outside of oval B. So that's 9, 12, 11, 10, and 8. There are 5 options out of my 12 total. That doesn't reduce, so we would just leave that alone. Now, sometimes your data is going to be given to you as a table. So here we have a DJ with 200 songs in their library for a party. We have some country, we have some hip hop, we have some pop, we have some R&B. And a guest selects a song at random, okay? Find the probability of each event expressed as a percent. The first event being the song is a country song, okay? So first it might help to know how many total we have. That's given to us. Thankfully, there are a total of 200 songs in this library. If I'm randomly choosing a country song, I'm going to look at the country column. There are 26 of those out of 200 total. So it's a 26 out of 200. I can put that in the calculator, or I can convert that to a percent myself by making that 13 over 100, which is 13%. Okay. The next probability is the probability that the song is a hip hop or a pop song. When we have an or situation like this and we're combining 2 things, we're going to add their 2 results. So here there are 60 hip hop options and 72 pop options. I'm going to add 60 and 72 out of my total 200 options and convert that to a percent, and we get 66%. And then finally, the song is not R&B. So your option is to either take your total and subtract the R&B songs, or you could add up 26, 60, and 72, because those are the ones that are not R&B, and then take that out of 200, convert it to a percent, and either way we get 79%. Okay? Let me know if you have any questions.